So this is a question from GATE 2023, question number 12. Let R cube be a topological space with usual topology, means from the Euclidean norm. And Q the set of all rational numbers. Define subspace X, Y, Z of R cube as follows. X is defined as those X mod plus Y mod plus Z Q belongs to is a rational number, and Y is those X, Y, Z is equal to 1. Z are those x square plus y square plus z square is equal to 1. W is equal to x, y, z such that x, y, z is equal to 0. Which of the following statements are true? We need to check which of them are homomorphic to each other. So we are going to use here some results that homomorphic spaces preserve connected components. Number of I think everyone is aware about connected components. If they're not, this let us just take an example. Y is equal to A union B, say, where A is like this and B is like this. So this is a disconnected set. Why? Because these are not connected. But A is fully connected, B is fully connected. So these are the components, connected components. This is probably the easy way I can tell right now. So homomorphism preserve number of connected components. So components like this are preserved. And yes, I think this is enough. And yes, second is that homomorphic homeo so homeomorphic image of a connected set is connected, means connected sets are homomorphic to each other only. Means if two sets are homomorphic to each other and one is connected, then other must be also connected. This is what this means, is connected. So we are going to use these two properties. So first is question about X is homomorphic to Y or not. Let me write again X. X is XYZ such that X plus Y plus Z belongs to Q, and Y is such that those XYZ such that XYZ is equal to 1. That XYZ is equal to 1. Okay. First of all, how does Y look like? XYZ is equal to 1. Note that if Z is equal to 0, not possible, because this whole will be 0 and we cannot have 1. So this shows that it cannot, like if this is X and this is Y, this is Z, so Z is equal to 0, this on this plane this graph doesn't exist, and similarly along this plane along X is equal to 0, Y is equal to 0, it does not exist. So it's somehow look like this. It is there, it is in there, it is in there, but it does not intersect here. So it has connected components like this, and each coordinate has 8 connected components. While we consider this is not a connected space at all. How to show this? Okay, let's consider a function continuous phi x y z, which is equal to x plus y plus z. This is a continuous function. This is composition of modulus and projection, then addition of continuous function. Therefore, it is a continuous function. As being composition and addition of continuous functions. Let me rewrite again. This is xyz such that x mod plus y mod plus z mod belongs to Q. Okay, so we have a function like phi xyz is equal to x mod plus y mod plus z mod is continuous function. Now its image, we know that continuous image of a connected set is connected. But what is the image of phi x? This is only Q. This is a subset of Q. Which is not a connected set. So X is not connected and it has no connected component because no subset of Q is connected. Q is totally disconnected. Thus it has no connected component. X has no connected component while we have seen that Y does have 8 connected components, so they cannot be homeomorphic. Not homeomorphic. So this is incorrect. Now we consider Z and W. This Z and this W. Z is x, y, z such that x square plus y square plus z square is equal to 1. W is those x, y, z such that x, y, z is equal to 0. Okay, this is a sphere and these are the lines. You can just see that all these lines, this is W and this is the sphere, this is Z. Now just observe that if we just take out this element, then how does it look like? It look like this. Now it's become disconnected. But if we remove one element from this, let's say this point, it's still connected. Thus, there cannot be any homeomorphism between them. Because if there exists a phi such that from Z to W, a homeomorphism, then phi, when we just remove the elements, any element from this is restriction of phi on this set, should also be this should also be a homomorphism. But we have seen that this is not true. This is not true because after we remove an element from here, this does not is still homomorphism from this. If two sets are homomorphism, then removing some elements also we should have, they must be homomorphic to each other. But when we remove an element from here and corresponding whatever whose image is this will also be removed, then these two are not homomorphic. So these sets cannot be homomorphic. Because even after removing some element from this and their corresponding image from this, if there exists homomorphism, then there still must be a homomorphism, but it does not, because this restriction to continuous map is also an homomorphism. So Z is not homomorphic to W. Y is homomorphic to W or not? Y and Z, we have seen that Y is not connected while W is connected, so this cannot be possible. So only last option is X is not homomorphic to W, which is true because this is a connected set and this is not connected.